I know it was a little bit too close to the NSF site visit, but Roger and I, Roger over there, we had a conversation when we were at the UC CEIN as we are beginning to move into new materials, in particular these carbon nanotubes. What did we know about them, and could we share some of the information with everybody? Because some of us are just getting up to speed on some of these materials too. The idea was to talk about these different materials, what we know so far, what we may not know, and really have more as a conversation rather than just a strict presentation. So I am going to go through a number of slides, but hopefully we'll have questions and contributions from different of you as you are beginning to work with these materials or have questions on how to work with the materials. And Sam and Shannon contribute with a number of slides and help with some of the information that I gathered, so I wanted to thank them as well for that. So thanks a lot. Sam's not here present here, but he's online and had a family medical situation he had to take care of, so he prepared those slides ahead of time for me. So thanks, Sam. Okay, so these are the carbon nanotubes, and we've seen some of these pictures. These are the pretty pictures of what a carbon nanotube should look like, a single wall and a multi-wall. And then these are images that we did actually a couple years, 3 years ago, of what they actually do look like. So in reality, once you disperse them, they are not necessarily straight, and we'll show you later on they can be very different from being straight. And so they are, and these are actually pretty unique images because we actually see individual tubes or close to individual tubes where the diameter may be just a few nanometers, and they're about a few microns long. And so that's typical aspect ratio, single wall and multi-wall. The multi-wall may have 20 or 30 nanometers in diameter for that particular image. This is more what you typically see. So if you actually looked at them, this is SEM, but you'd see a match, and that would be the more common thing. And the question is, what will we see in terms of environmental applications? It may be unlikely that we see them as individual ones, but we may under some particular concentrations. But again, most likely we'll see them in this fashion. So what's the big deal? Well, they have superb mechanical, optical, and electrical properties. They're really very, very strong, and so that makes their mechanical use for structural products, and I'll show you some examples a little later. Really, really interesting. Optical, they can capture photons, they can re-emit them, and also they can conduct to some extent, so they are semiconductors, and that has a lot of people very excited about to be able to store information, capture photons from solar power to be able to do energy applications, other medical applications that people are thinking about. So there's a number of things that people are working on. And very large surface area, so this is a material that was going to be very, very interactive with anything we put it in contact with. Typically very hydrophobic surfaces because it's basically just a carbon surface, so it will be hydrophobic, but as we'll see, that can be changed. And then you can functionalize them. And so, Hunter, what does that mean? No, I'm not picking on Hunter. So we can add, we can add functional groups to them. And what we mean by that is that you could have, for example, carboxyls are typical. So you may oxidize the surface a little bit so the carbon has a few oxygens present, and that will help it to both get into water to disperse well, and also for other interactions they may be interested in. Amines could also be some of the functional groups. But they have this issue that they tend to aggregate when dispersed, not to form aggregates when dispersed. And I'm going to jump a little bit just to show you some examples of what can be done with some of these carbon nanotubes in terms of materials for real applications. So this is a presentation from Nanocomp. It's a manufacturer of tubes and of different yarns and sheets of carbon nanotubes. So what they're doing here is they take their carbon nanotubes, they put them into this system here, which is going to basically align them, and at the end of that product, what you get is, let me see how this is going to work, sheets. So you can get sheets, or you can also make yarns out of these things, and the sheets can be of different dimensions in terms of both, their length, width, but the thickness can be a few nanometers, and so that can be done. And also, here's some other examples, very, very long lengths. So some of these are being used for structural development of wings or other surfaces for aircraft. some of the new aircraft are using these materials for strength. And also in terms of, that's another application. Another one would be making yarn. And so same type of approach, but instead of coming up with a sheet, you're rolling it into a yarn. And so it makes these very long spools, which can be used in the place of optical fibers and other such applications. So some really interesting applications for these materials. And they can make them different gauges or different diameters and different strengths as needed for all of these applications. So they can make kilometers worth of these materials. So they are going to be used in applications which may have environmental significance. And from a life cycle perspective, that's something we need to be thinking about. What are some of those potential applications? Okay. Any questions? So I'm going to go back to the PowerPoint. So we have these properties that are really cool. The ones we're working with are from 3 different manufacturers, and these guys use this particular process, and I'll explain what that process is all about and why then we get the impurities that we have. So the ComoCat process, the HIPCO process, and then Carbon Solutions uses a different process. It's a purification process on the HIPCO. So they're basically using HIPCO and then purifying it a little bit. And we here are getting 2 different types, so-called as prepared or as synthesized. And then the other one is purified. So we have, for some of these purified materials, ComoCat, we don't have anything more than the one we've got. And at UCLA, they also have one which is in pluronic acids or pluronic media to be able to disperse them and look at lung tissue impacts. Yeah?
So what is purified? What changes?
Let's talk a little bit about that. They are trying to, there's several things, but I'll touch on it in a little second, so let me just go a few more slides. That's a really good question. So this ComoCat process is basically a cobalt and molybdenum catalyst that they use. They are basically taking the carbon monoxide, so it's carbon monoxide that comes into the process, so incomplete part of the combustion, and then at high temperature and pressure, you can, with the presence of the catalyst, begin to generate the carbon nanotubes. So it basically breaks apart into carbon and carbon dioxide, so it disproportionates. And then at the end of the process, you're making the product, so you're making these. And excess gas comes out, they remove the CO2, they recycle carbon monoxide, they add up a little bit more, and it comes back in there. And although the catalyst is tended to be just to promote this reaction, it does get incorporated to some extent into the carbon nanotubes. So part of the impurities, going back to Shital's question, is to remove some of this excess catalyst that gets incorporated in there. So part of that we'll see is they'll have some catalyst embedded in the carbon nanotube. So it's a metal impurity. The other impurity is you don't just make carbon nanotubes, you make all sorts of products. And includes graphene, fullerenes, and other things. Carbon black, and other materials which are not what you intend. So those have to be removed one way or another. So that's the other impurity there. The HIPCO process is basically taking and, again, starting with carbon monoxide, you deposit it onto a surface and you make very thin layers, and then at high temperature and high pressure, in the presence of iron, and these are basically just iron clusters there, then it breaks down again into carbon and forms the carbon nanotube and CO2 as the other product. The iron is added to the gas, so it goes into the gas phase, and it helps to, first it decomposes and then makes the condensation points for the formation of the carbon nanotubes. And so as you start adding that, you get carbon monoxide plus carbon monoxide forming dioxide and the single wall carbon nanotubes. Sometimes they also use nickel as a catalyst, so it can be iron or nickel. And that will explain why we get some of the impurities, again, in their materials that we have. This air oxidation process, so this is what P2 uses. We have 3 manufacturers. One was the ComoCat, the other one was the HIPCO, and then P2 is HIPCO plus air oxidation. What they do here is the original materials produce a lot of garbage. 30 to 70% of the product is impurities, which is a fairly large number. Metals, amorphous carbon, so all sorts of carbon black and other stuff, fullerenes and so-called bucky onions. People get very creative with lunch going here. So bucky onions. And you can wash them with acids, but those tend to functionalize the carbon nanotube. So if that's not what you want just carbon, then that's not a good solution. Sometimes you do want to functionalize it, but if you don't, what you do is oxidize them in the presence of air at a particular temperature, and it tends to attack more everything else but the carbon nanotubes. They tend to be fairly stable to air oxidation, and so what they do is oxidize everything else, and therefore being able to remove those in the water phase. And so that's one way to do it. And then they may add some other washing to remove some of the metals, usually HCl. So based on that, that's why we get these properties in terms of the metals that they come here. So Comocat that we have has cobalt and molybdenum. This one is already as is, so we don't have any more purification. And it's about 5%, 5.38% metal. And so that's something to consider in terms of what may be some of the toxicological implications. Then we have the HITCO as received and purified, and you can see that that is mostly iron because of the catalyst that gets used. And it starts out at 31% and drops to 16%, so that's the main impurity there. The AP comes in at 44% metal, and then they purify it to 2% or so, and that's basically nickel and a little bit of yttrium. So that's the main implications for that. Any questions? Yeah, Trish. So that's so this is the total metal in the carbon nanotube. Then this is the mass that goes into that, and then if you look at this and say the 5.38%, 88% of this is molybdenum, and 12% of this is cobalt. Yeah, that's why these are 100%, so they don't have anything else, and then this is the balance between yttrium and nickel. Sure. Any other questions? Yeah.
What does functionalize mean exactly?
So you came a little late, but that's all right. So, now I'm just going to be able to tell you. No, so basically you may want to have a carboxyl group, so maybe a carbon with an oxygen or an oxygen and an OH group, so an acidic type group, or it may be an amine type group, depending on what you want to do with the carbon nanotube. Sometimes it's basically just to try out different approaches. Sometimes for medicine, they're using these to help them put them into solution, to disperse them. Sometimes it's because you have a particular reactivity of that and that you want to exploit.
I meant with the acid.
The acid may, yes, the acid will oxidize it. The acid will oxidize it and begin to form some of these carboxyl or other groups on the surface. So it oxidizes a little bit the surface. Sometimes it's just an OH group, alcohol group. Sometimes it's a little bit more complex. Okay. The other thing that we have to consider, which we haven't done much in terms of what the effect may be, but it's what's called a chirality, or how you actually form the carbon nanotube. So you could form it, basically along different axes of the original structure, and they have, for example, this one here with this oriented this way, which forms what they call a zigzag form, and then this one here is an arm-chair form. So there's different angles that you can create them, and we don't quite know actually what the ones we have are, but that's something that may be coming down the pipeline, and we may have to think about chirality as a function. And I try to sort of get some better idea of what that may mean. It's hard to really see the difference, but certainly you can see that the way that these may interact with something approaching the surface may be somewhat different depending on how they actually come in. So they are semiconductors, and so when we look at their spectra, so if we put them in the spectrophotometer, what we see is that there are a number of so-called semiconductor transitions and others here, which means that you can have a photon being picked up by the carbon nanotube, and then it gets excited, so it breaks it up, and that all these different jumps to excited states from the original energy state to the conductive energy state, the valence to the conductive, can generate a number of transitions. So you can We basically capture photons, and then pass that energy out in different ways. And so that may have some implications for toxicology in terms of transferring that energy to target molecules, biomolecules, or other things. Yeah.
Did they try to compare this to silica?
Silica.
How semiconducting is?
Yes, silica by itself generally has to be, it's better to add something, a dopant, so that you can get better conduction on it. Otherwise, if you just have the silica, it may not be a very good semiconductor. So when you add different dopants, so you disturb the crystal structure, you actually get more semiconductor properties. But this is very weak compared to what you may see. So this is not a very good semiconductor as far as I can see. I may be wrong, but my thought is that those jumps should be bigger for you to see it. Titanium dioxide or cadmium selenide are other semiconductors where you see the band gap being right there and very active, very photoactive. Yeah, Roger.
So what is that? What exactly is that spectrum?
So we're seeing the absorbance of photons of different wavelengths, and this is basically actually electromagnetic radiation, because some of these are down in, this is UV, and that's way up there. And so it's the absorption of these different electromagnetic radiations and how strongly they absorb. So they absorb very strongly at this range, and then it drops off, and then there's this whole wide range here, which is apparently just a lot of interactions with that radiation at that point.
So why, given the sharp peaks in the inset, why, I wouldn't even notice the bumps in the spectrum had you not put arrows.
Yes, true, and these are interesting because they're in the visible range. So that makes them interesting because they are where sunlight and other radiation may interact with them. These other ones here may not be as relevant, or may not be as relevant for different applications. But we'll see also if that's also used to look at purity and whether when you disperse it, you actually have it dispersed properly. So that's what the spectrum is also used for, that type of. Yeah.
If these are such sharp levels and precisions, why are you
not seeing a much sharper peak? That's why it's I think at least in this range here, they do have some transitions, but they're not very strong. I think there's some other peaks that are much stronger. So I think you're right. Yeah.
So just to clarify, this is a natural process and not external stimulus.
No, it's an external input, so you are radiating it, some electromagnetic radiation, either in the visible, in the UV, or infrared, or even further down. And so it is an external stimuli, and it's absorbing it, and then that's what you see in terms of the spectra for that absorption.
And is that band, I mean, you sort of band gap in the middle there, is that dependent on the structure of the material and the impurities?
Yes, that's for sure. The other one that is this other one here is another characterization, and just suffice it to say that this particular absorption peak right here is very reflective of a graphite-like structure. So you would expect to have very strong peaks, and you see it here for carbon nanotubes. So if you're able to disperse your tubes well, that should be very sharp, and we'll talk about that later. And then this other D band here that is seen here is also typical of carbon nanotubes, and if you don't see it, it may be that you don't have carbon nanotubes. So it gives you some information, this ratio of how much integrity there is in your carbon nanotubes. So those are just additional features. Some of these other ones also help to get an idea of the size of the carbon nanotubes or diameter, so people use this information for that. So there's different dispersion methods. This is a study that was done in 2007 by other people. And what they were looking at using different surfactants. So SDBS, sodium dibenzene sulfonate, is a very common surfactant. It's used for dispersing many different things that are hard to put into water. Sodium dosabyl sulfate is also another very common one, SDS. DNA, where these guys use DNA. I crossed two because they're not relevant. And then the fifth one is carbon nanotubes in water. So we see here, for example, again, the absorption And these are the spectra, and this is the absorption for SDBS, then the other one's for SDS, DNA, and then water. So in water, you see, first of all, there's basically no absorption, which means it really did not disperse well. And when you look at the image, a little better in my image, but there's nothing in the water, very little. So it was not a good dispersion, which is not surprising. These other ones show they're well dispersed, but that's where one begins to look at, do you get these transitions? And if there's nothing there, maybe that you weren't able to do a very good dispersion. In other words, you don't have a very high concentration dispersed in the particular suspension. And then these are other, this is a study that was done by this other group looking at dispersing using gamma arabic, PVP, so a polymer, natural organic matter at 2 different pHs, tritonitrous, another surfactant, and then this sugar amylose that was also used. And so they used them, and you can see that they can get different concentrations depending on the dispersants. So it's a study to see which are better dispersants than others. For the same amount of carbon nanotubes put in there, some of these are really good dispersants. Some of them are so-so, and some of them are not all that good. It's also pH dependent for the organic matter. That's because organic matter has a lot of these functional groups, and so it will interact with the carbon nanotube differently depending on the pH. This is the concentration that they were able to get, the diameter. So sometimes you're able to disperse them, but the diameters may be quite different. So that means that they're actually aggregated to some extent. These diameters are what you see with light scattering, and so you get some different sizes for the different types of carbon nanotubes. So even though this one here was not as good as an overall dispersant, it was good in terms of the effective diameter that they were able to use. And also here are some of the charges on those carbon nanotubes, which vary. So the charge on the carbon nanotube varies depending on the type of dispersant you may use. Yeah.
Would alginate potentially?
I'll show you. Not very successful so far with alginate, but yeah, we tried it. So basically what it means here is that the charge is going to be very dependent on what you use to disperse them, not so much on the carbon nanotubes themselves. So a couple of years ago, 3 years now, Peng Wang, a student working with me, began to look at dispersing carbon nanotubes. And what we saw was that with humic acid, we were able to do some very good dispersions of them. And that the fact that there's plenty of humic acid in most freshwater systems and in many seawater saline systems, it's very likely that you get good natural dispersions of these. And then we can see, for example, the concentration is a function of the humic acid concentration. So it does respond to that, but it also saturates. So if you can't just keep adding and adding more humic acid, you just don't get more bang for your buck. The good news is that most concentrations in the environment are in this range here, in the lower range. So we're nowhere close to saturating them. It's only in very, very high humic acid conditions, which may happen in an algal bloom or other environments. So it's not impossible, but it's just not as common for, well, I shouldn't say whether it's common or not. We may find them. And then the charge and how well dispersed depends on the type of ion that's present there. So calcium and divalent ions tend to have a less negative because they are basically surrounded by a lot of positive charges, whereas sodium and potassium tend to lead to more negative dispersed carbon nanotubes. So these are less likely to aggregate here. So one of the ideas is that it's a hydrophobic interaction. We have humic acid, and humic acid basically will have kind of a hydrophilic head and then a hydrophobic tail, so like a natural surfactant. And so these attach onto the carbon nanotubes, and then these expose these more soluble heads to the rest of the water, the media, and so that's what allows them to get well dispersed. This is dispersing in natural media, so this is work that Sam's been doing And so what we've seen is that they disperse well in NOM, so natural organic matter, and it depends a bit on the type of carbon nanotube. Some of them disperse really well, and we get very small sizes. Others, like that HIPCO, the raw HIPCO, does not. I'm still kind of baffled because the raw HIPCO has more metal, and metals should help the carbon nanotubes to actually disperse, but we haven't seen that that works very well. It may be that there's other interactions. And so we see here again, the HIPCO raw has a pretty clear dispersion, or suspension is very clear, so you don't see the concentrations going up very high. And then this is alginate, and going back to Hunter's question, so far it doesn't work well. As just alginate, what we get is these very, very large sizes. These sizes are, you have to sort of think what you're really seeing, because a particular carbon tube may not have this particular dimension. This is kind of an instrument is trying to average a very thin diameter with a very long fiber, and so this number is really reflective of what the light may interact with that particular tube. But smaller dimensions, we really should just call it dimensions, are a better indication of better dispersion than these very large ones. So clearly, these are not successful so far.
Are those pictures of the supernatant also?
Those are the pictures of the supernatant, and what we've seen, or what Sam has seen, is that you get some aggregates that pops it out, and you have to get rid of them, and some films of carbon nanotubes at the top, which you also have to get rid of, and so you get both of those, and those films are, may have other implications, but yes.
Is CERN try varying the concentration of the carbon nanotubes?
No, so far right now it's just been the same amount of carbon nanotube and the same amount of the dispersion with different types of carbon nanotubes, just to see what works, and still working on improving this. In fact, Yemi is going to be working on this during the summer, so part of that work will be done by Yemi. Yeah.
What is SG65?
SG65 is the Comocast. That's Comocast. So this is the Comocast, the HIPCO, and the P2.
And NOM was just a humic acid?
This one is actually Suwannee River natural organic matter, which is a bigger part of the whole organic matter than humic acid, which is just that fraction.
It's very high in humic acid, though, right?
It's high in humic acid, right? And there's been, some criticism about using that because of that. And its humic acid is different than other humic acids, but it's a kind of well-used reference in materials. Sam's also been spending some time on this method where he first disperses them in toluene, so takes the carbon nanotubes and puts them into toluene, and then after they've been well dispersed in toluene, he puts that in contact with water. They transfer to the water, and then he eliminates the toluene by volatilization. And in principle, we see from the spectroscopic analysis that there's very little or no toluene left behind. And then you can add the alginate, then you can add other things, and they remain well dispersed. So that may be a two-step process, but it's still a question whether the toluene will have some or no implication. And so what we see is that their size kind of is in a range that we would like to see most of them. This is the size distribution, really. So what we're seeing is that there's a whole sort of, this is the wavelength, and this is the size distribution. So it refers to that one over here. And so we see that, the carbon nanotubes are in the order of a few, like 200 nanometers. And then this is showing concentration, really, over time. So days 0, 1, 2, 3, and 22. So after 22 days, the concentrations are pretty much the same as we saw initially. So it's very stable. It's not changing much, which is what we want to see. These other NOM dispersions, they do sell out after a few days, so something to keep in mind that it's not a very, it's stable, but it's not as stable as we would like it. And then just some images. And here also, basically, it shows very high G to D ratio, showing that the carbon nanotubes have not been affected by the method of dispersion, whereas this one here, the HIPCO pure, has a very poor G to D ratio, so it has been affected.
So this is toluene mixed with water?
Toluene we mix with water, and then you volatilize the toluene completely, so that at the end you're left just with carbon nanotubes in the water.
What is the primary? Can you remind me what the primary size is and how the shape of the particles affects that measurement?
Right. The primary size is a few nanometers, so on the order of about 5 to 7 nanometers in diameter, and about it ranges from 700 to 1500 nanometers in length. So that's why this.
So this is like an
kind of an average out. Yeah.
Sort of.
Right. Kind of a weird average. Still trying to figure out. And the more interesting thing is that when we discuss them, you'll see they look kind of funny. Anyway, so they can be stabilized in seawater. So we have them dispersed in toluene and then followed by seawater. And so they remain fairly well dispersed in seawater if we follow that method. And then sonicated directly into seawater, they aggregate fairly rapidly. So just putting them and sonicating them doesn't work. Alginate doesn't work very well, but this one seems to work better.
So that toluene method, that's not sonicated?
It's not sonicated once it goes into the seawater. So the only interesting feature was that Sam recently with Milka took a look at some images of these carbon nanotubes, and what we found was that they were not tubes anymore. They formed these rings or donuts or nanotori, and so we found out that, in fact, first we thought maybe this was completely new, but no, there's a couple papers in the literature that show that people get them, and they're theoretically supposed to occur, and then some people have shown that they do occur. So it's quite an interesting finding. It seems to be pretty reproducible, so they do always form these structures. So what it looks like is that they go end to end. So the tube completely wraps around and forms a full donut. And it may have some interesting magnetic properties, so something to think about. So we're rethinking whether the toluene method, but it's not an interesting method of dispersion. It just may lead to some very interesting structures. Yeah.
Is it reversible?
Good question. I don't know yet.
That doesn't happen when you don't have toluene?
No.
Oh. So all the different types of carbon nanotubes?
A couple of them, not all of them. Perhaps we haven't seen every one of them, but as far as I've seen, I think 2 or 3 of them, of the 5, do form these. Yeah.
It makes a big difference if we're thinking that the injury will come from stabbing the stone.
Yes, right. And that may be that this method leads to no injury, or at least reduced injury, because it's not in the same shape.
But we have to do it to disperse it.
We have to do something, but that's where it just, so we now have to, we're rethinking whether this method, this method may be interesting for some applications, but it may not be the best method if you want to see, how it may puncture. Yeah. Yeah, so this is about 100 nanometers there. So that, we measured that was about 150. And if you do the diameter, it coincides with the, not the diameter, the circumference, it coincides with the mean size of the tubes. That's where we sort of are estimating that it is one tube that comes around and wraps around. It has to be a bundle because this is about, well, I think it's about 30 nanometers. So it may be a few tubes that are bundled together. Yeah. Yep. It could unravel. Yeah. So there may be some interesting. I mean, I don't think we should say no to nanodonuts, but we may have. Yes. These were all single wall carbon nanotubes. Yeah.
Has anybody reported that they do unravel and you should look at the
No. No. The answer is no. The reports have only been of their actual presence. But no one's actually looked at their toxicity at all, and no one's looked at whether they unravel under different. So those are all really good questions. I hope Sam is writing some of these down, and then we should all work on those. No, I think we went with toluene just because non-carcinogen, so we thought it'd be easier to work with. But it could be that just the aromatic ring works. We're thinking that the interaction is between the carbon nanotube and the aromatic ring, and the pi-pi interactions that are really basically helping it to get into the suspension. That's our theory, and we're sticking with it. And then I showed this at the site visits, where showing that this was the original intent to see whether they were photoactive, and we see that they are photoactive. So this is basically indicates that we have good photoactivity for the purified, not very good for the raw. So the raw does not have the same level of photoactivity, and this is HIPCO. This is the bare P2, which is a purified one, so again, shows very strongly that we have good photoactivity. And then we have NOM that seems to decrease. So it coats it and may interact with the photons that are coming into that way. Or it may be that they both pick up the photons, but then they get shuttled, and so they're not available for photoactivity.
The scale on that one, though, is
a lot bigger.
Yeah.
Yeah, this goes, 50,000, 100,000. This is
So that's 100,000.
100,000. This was quite big. That one is the one that kind of people said we should put them all on the same scale because
it was over
that was
100,000 actually.
yeah. This is actually 150. That's 300,000. So we should put them on the same scale so one gets the right perspective.
So what wavelength?
Good question for Sam.
Okay.
Yeah.
I was just thinking because
I think it's natural sunlight. Sorry, it's natural sunlight. So all this was with the pheno map, but it's basically the full spectrum.
okay. Because for titanium, at least like they have actually used nickel and iron intentionally as a dopant to shoot
Yes.
the
Right.
band gap.
Right.
So,
And there are people who have been using titanium-doped carbon nanotubes also to have for water treatment approaches, applications. So, but yeah, so one can do that type of thing. So. Again, this is work that we did a while ago, but one of the questions is, how do the carbon nanotubes distribute in the environment? How do they partition between water and the organic phase? So what we saw here was that if you have the carbon nanotubes in humic acid in water, they're well dispersed. If you add toluene and you still have the carbon nanotubes in humic acids, the carbon nanotubes tend to be hydrophilic, so they remain in the water. If you only have toluene, water, and carbon nanotubes with no humic acid, then the carbon nanotubes tend to go that way. So that was early work, and then we've seen that you can get them in here and then evaporate off the toluene. So, but that means that if they're in the environment and they do come into contact with organics, natural organic matter, or other organics present, biota, microbes, they may partition well into that organic phase if they're coated with humic acid or other dispersants.
usually do they really have an affinity for the interface? It looks like that really water interface here.
They may have an affinity for the interface because that usually is for a lot of colloids. It's a lower energy state to be at the interface. So and that's why also when we form them, sometimes you get these films of carbon nanotubes that are at the surface. Yes. There's also a little bit of this. Always you get, even if there was no carbon nanotubes, you also always see a little bit of darkening just because it's a thick interface.
So is that, I'm sorry, with the humic acid, is that the same thing that's going to happen if you oxidize them with acid? Or?
Yes, it'll be similar. That's correct. That's correct. And then this was work also that where we saw that those carbon nanotubes that are dispersed with humic acid can transport through porous media, so soils or sediments. They do transport, and so we do see them breaking through in this particular soil column. And even though they have this, the particular shape, they do find their way through it. They do get reduced, so this is a particular condition that's leads to fairly stable and high transport. But some of these other conditions lead to a lot more removal. So under higher ionic strength, not too high, this was more like groundwater, and high, mostly calcium chloride, or high hardness, then you would see a lot of removal. So still need to work on that, but it means that they are mobile in the environment. So now carbon nanotubes toxicity, and it was both Shannon and Jenny provided some information that Shannon then also prepared this. So some of the ideas are that mechanisms of toxicity may include physical puncturing. So that's one idea. And so the idea is that they can actually puncture the cells. Others may be brought in, and be brought in tangles, and it could be those donuts that may also be brought in and via phagocytosis. You would then have it in there. And once inside, they may have some ROS generation. Now, the ROS is something that has not been observed in the medical literature so far. So people have looked for ROS and have not seen that. But it may be that in the presence of light and for some of our unicellular organisms, we may see some of that. And that may be interesting to look at that. These were multi-wall carbon nanotubes dispersed in saline with a surfactant. So twine is a common surfactant. And then they put that into the lungs of the rat. So it helps to disperse them, and then under those conditions. And they do see them coming in and finding there, and so they have an inflammatory response with that. Yeah. So that's the other one was these copepods. So learning all these organisms. So these deposit-feeding entering copepods are exposed to different ones. So as prepared with no functionalization or oxidized or other materials, they show different implications. So what they see here is increased mortality at high concentrations for the current materials or the as prepared, but not with the purified. So in this particular study, the purification helped. So it could be the metals that were reduced and that reduce some of the implications. And then copepods do ingest them, but excrete them as fecal pellets. And some images there. This is Daphnia exposed to lipid-coated carbon nanotubes, so some fatty acid coating. And they did use them as a food source, the coating as a food source. But they did show mortality at higher concentrations, so something to think about. And they tend to precipitate in the presence of Daphnia, which it may be that the Daphnia eat the coating and reduce then the dispersibility, and then they aggregate and settle out. In a good way.
So I think for those donuts, it would be interesting to either give them to Daphnia or copepods, because then we can collect the fecal pellets and
see whether did they get unwrapped. Could you find that's really cool.
Gone through the digestive tract, unlike the mussels where they could
or amphipods, any one of those organs would be great.
I'm curious to see what the direct effects are on ingestion. Is this like low metals number? So that they're not filter feeding, right? So a lot of stuff that flows on the feeding shut down ingestion, which has a much bigger effect.
And actually, I don't know if it was this one, a different paper that actually showed that if you give them normal foods, you can clear the gut pretty fast.
Okay.
It's slower than normal just food
feeding, but they do clear them out. But it would be interesting because, from our perspective, even if they just take them in and put them out, that already makes them perhaps more available to other organisms. So at least it moves them down the food chain, so something to keep in mind where that may lead to other interactions here.
Coating them with lipids seems like a good way to get all the metals into the copepod.
Right.
And if I understood right, these are soluble.
They said soluble, and I took it off because I think they meant dispersible. But they said, well, maybe that the lipid is soluble. Is that what the meaning was?
They said these once coated with this stuff, they're soluble. And then,
I think they meant dispersible, and that's why I changed it. I used to say soluble here, and I changed it because I think they meant dispersible. And lipids, I don't see lipids being very soluble, but and I think it's a common mistake.
And I think it's great to bring it up. It's what you also see in the literature too, and in the other particles.
A lot of people talk about the solubility. It's just wrong.
can you go to the chocolate?
So also rainbow trout dispersed in that surfactant I talked about before, the SDS, and then sonicated for 2 hours. And so what they see is a respiratory toxicant for the trout, and then see some effects on ventilation rates and secretion. And even though you saw that, they didn't see oxidative stress. So again, not a lot of evidence for ROS from these guys. and also thickening of the lamella. Is there a question or a comment, Trish? Gil. It's good to have the experts here. Okay, so last one is the zebrafish embryos, and this was a study by Cheng et al. But I understand Andrew's also been working with them, and we just didn't have the data with us. But so zebrafish embryos also show some interactions. These were fluorescent and BSA functionalized multi-wall carbon nanotubes. So I don't think they really mean functionalized. They're made more dispersed in BSA, and so that is a way of getting into the suspension. But they're fluorescent, so that may also affect to some extent their interaction with the organisms. But then you can then see where they end up. So there are some benefits to having the fluorescence tag. It's just a question of whether it affects too much the actual. And so they saw, accumulation and some effect, but they do clear out, and maybe something interesting to keep in mind. So any more questions? That was just to give you kind of an overall. Let me see if there's any questions from the other side. Any questions from anybody else watching the presentation?
Can you repeat the question to
Yes. Right. Thank you. So any questions here while we're waiting to see? If you want to type in a question, if you can, if you're interested. Or any other questions here, Trish?
When you're working with these materials that have a pretty significant metal content, should we be thinking about some kind of metal control? Or, how should we be thinking about the bioavailability?
Right. So the question that Trish is posing is, as we use these materials and we want to see how toxic they may be, one way to see whether the metal toxicity is a big factor is to perhaps consider a control which has the same concentration of metals present, so that you could see whether it's just the metals or are there other implications. So I think that's something that it's good to bring up, because I think we should have those controls as we report these results, toxicity results, and even other results, just to see, are some of the other physical, chemical behaviors we see related to the metals, or are they related to other things that may be present? Yeah.
On a similar question, do you know how the metals are incorporated into the carbon nanotubes?
Yeah, it seems that they're pretty much very strongly bound into the structure, because even we saw some of the preparation steps that they have still leave you with a fairly high level of metals. So even though they've been purified, you still have, in some cases, 5%, 60%, or 2% metals. And that's been after someone's tried a lot of hard work on purifying them.
Incorporated into
the carbon nanotube structure. So they may be covalently bound to the carbon nanotubes.
Within the
my guess is that most of it is, the part that's left behind is really hard to remove, and therefore it's not something you can dissolve just with acid without changing the nature of the carbon nanotubes. Yeah. So sorry. So the question was whether these metals are strongly bound or not, and that's my thoughts. Oh, okay. Saji, has anyone looked at the phototoxicity of no, and we are beginning to ask that question, Saji. So the question is phototoxicity of these nanotori, and we're just getting to that point, but certainly it's something quite interesting, and we'd love to share some of these with you so that we can run them through the HTS and see if there's any potential implications.
Are they stable?
Yeah, well, they seem to remain stable in the light. But the question is, and 20-some days, so they don't seem to be being affected by it. Hunter?
Based on the information we've seen, were there more pros than cons about pushing forward for toxicity studies across a wide spectrum of organisms, or do they seem like they're just so stable and you have to do so many, just so many hurdles just to get distortion?
Right. So the question is, based on the information we have so far, does it look like it's an interesting area of research to look at the toxicity of these different carbon nanotubes and their implications? And my answer would be yes, in part because I think they're the ones that are more likely to show real nano effects more than other materials. A lot of the other materials that we've been working with, a lot of what we've seen in terms of toxicity has been the dissolution of metals, and those are the ones that then cause the toxicity. There's some where we have seen some of the work where we see the titanium dioxide attaching to the cell and then the UV light affecting it. So there are others where we do see that. But this is, the carbon nanotubes, I think, will have some interesting toxicological paradigms to test. Now, whether we'll see all of those or not, but I think it gives you something to really look at that nano effect, potential nano effect. Other.
It also strikes me, I mean, it's been reported that there's stories that are found in nature and they've been discovered in nature, but these are probably about as synthetic as anything that we would be working with, right?
Yes.
Because there's natural analogs to titanium, zinc, and
right. So the comment was that these carbon nanotubes are they're kind of as synthesized, they're unique in terms of what we may find out there. So other materials that we've been working with, they're mainly natural analogs, and so this may be also interesting because of that uniqueness. Yeah. But, oh, sorry, Chito.
Okay, slightly different question. So in organic nano material, there is a breakdown at scalability at about 20 to 30 nanometers, and above that, at least that's from the recent, above that it's still scalable to their bulk counterpart. Is there some kind of trigger in carbon nanotubes where there is some kind of scalability, and at some point it just breaks down and completely different quantum effect or something else?
So I think just to sort of repeat the question, but also sort of put it as I understand it, is for many of these nanomaterials that we have, titanium dioxide, a lot of the metal oxides, some of the metals like silver nanoparticles, there seems to be kind of a really small scale, the 1 to 20 nanometers effects, and then the kind of more bulk-like effects that you see at a higher size. And so above 20 nanometers, or some people are trying to look at what is that threshold. And so for those materials, there seems to be a clear threshold. The question is whether we have a similar threshold for carbon nanotubes, and the answer is there's not enough evidence to show that there is a threshold for scalability. So we don't know if either these single tubes or mats of tubes or yarns of tubes will behave in a way that's bulk-like or not. I don't think that we'll see, for example, an analog would be carbon black, but carbon black is very, very different. So the structure is just not the same to be able to say that that's going to be a good proxy for what you would expect.
Yeah, no, I was not referring to the yarns or the sheets, because we are just talking about the free carbon nanotubes. So regardless of whether they're yarns or sheets, it's what matters in terms of free.
When they're free, right. So, right. But that's going to be a tube, and that's a question I think that we need to be answering. Is there a particular size or other dimension that, diameter or, some particular aspect ratio where it becomes more bulk-like or not? Yeah. There's a comment here that Saji says that they observe increase in the mucus level of rainbow trout epithelial cell line model developed recently when exposed to silver nanoparticles. But that's referring to his question of phototoxicity. Yeah, Bob.
I have a question, sort of two parts. One is, do we have any real information about how the particles will be introduced into the environment and what form? And basically, most of the focus has been on dispersal. And the reasons for that, as I see it, are two. One is that that may represent the worst-case scenario in terms of toxicity. And second, in terms of reproducibility, it's perhaps more desirable. But if in reality the particles are getting into the environment and floating on the surface, for example, or sinking to the bottom, then that may actually be the worst case scenario. That could actually be the worst case scenario.
Yeah.
And I was just wondering if we have any information on whether the particles are likely to disperse. Yeah.
Well, yeah, so the question is, do we know what are some of the potential emission routes for these different nanomaterials? And the answer is not a lot of good information, basically, particularly for the carbon nanotubes. But the image I'm showing here, the reason why I brought it up is that it shows first they make the sheet material, kind of a film. It's more like a mat. and then that goes into these molds that are basically then shaping it. Then it gets coated with epoxy, so they use an epoxy resin to make the shape, and then that goes into some of these aerospace applications. And you think, well, so what's the likelihood that that plane is actually going to be? But it may not be that you have to get that far. These manufacturers then have to machine these parts. So they drill them and all sorts of applications. And so far what we've seen is that they don't pay a lot of attention to how to dispose of them. So one possible route may be the disposal of some of these materials. And that may be... I'm trying to get a hold of some. And to see what's in it and what does the epoxy matrix do in terms of the tubes that may be exposed, and what do we get. So that may be one exposure route. Solar panels would be similar. People are using some of these for solar panels. And the question may be, as people install these, probably not during their use part, but either the installation part or at the disposal side. And that's, she calls here because she's working on life cycle questions and she's focusing on carbon nanotubes. So we hope to be answering those questions in the next few years. Yeah, so a couple of years, yeah. Yes?
Even more basic though, do we know what kind of carbon nanotubes are in these sheets?
We can get that information, yes. In fact, this nanocomp is now, we're trying to roll them into the CEIN and provide us with some of the materials, and so that we can begin to work with them. And they seem to be proactive both in terms of providing materials and also providing information for the life cycle. And so we have a call in July to sort of go over how are these materials being manufactured, distributed, used by their customers, so we begin to answer some of these questions on what really happens to the materials. Trish.
Other sort of solid phase pollutants, and really worried about them, and we like to very manufacturers and the raw materials. I'm really worried about what can release.
Yeah.
So phthalates.
Right.
So we might want to, I don't know, I mean, this is just carbon.
Yeah, right. So the question is, or the comment is whether, as we look at other materials, we see they're leaching, and in this case it's carbon, and it's a particular shape, but that type of thinking as to how are the potential abrasion would be a possibility. So as these materials get used and they get abraded, there could be some tubes that get exposed and get released, so that's another potential route. And I think those are questions that we need to think about for our renewal proposal. Talk about those, perhaps think about experiments that help us to address those, get some materials, put some under some accelerated aging type of applications, and then we see what happens to them. Do they break down? And if they break down, what gets released? And then maybe we begin to think about how do we do toxicity studies on those breakdown products. And so, okay, well, thank you very much, and lots of good questions. So, see you soon.